Hello, Revision 2021, and welcome to my seminar about the 8051 from a 6502 point of view. My name is Jens Schönfeld. I'm the CEO of Individual Computers GmbH in Germany. I grew up with the Commodore 64, like many of you did. I picked up 6502 assembly on the way, and later on I studied electrical engineering at the RWTH in Aachen, Germany. And I need to emphasize, I'm not a programmer, I'm a hardware guy, but I write code every now and then. And it's 6502 and 8051. First of all, why 8051? It's still an industry standard, enough of an industry standard that Synopsys is even still supporting it. A friend of mine works for Synopsys. Shout out to Kai if you're watching this. Famous quote from him: 8051 is said to violate human rights. Now, I hope to show that it's not all that bad, because modern implementations of the 8051 are surprisingly fast. There is a ton of development tools available. You can get free assemblers, compilers for just about any OS. And most of all, you can get really cheap chips with at any speed, with any amount of code space, memory available. The smallest one down to 3 cents only if you buy in volume. Some history about the 8051. It was released in 1980, and early 80s, of course, NMOS was the process to go for. It was released as a CMOS processor back then, later. It is available as a chip, as an actual chip that you can buy. It's also available as an IP core for synthesis on an FPGA, or if you want to make your own chip, an ASIC. These cores are either really small. The smallest I found is from Evertronics, Poland. Only takes 2,700 gates. Then this seminar is mostly about TSMC's 1T8051, which is probably around 10K gates, 10,000 gates. I haven't found any source of it, so this is an educated guess. But just as a comparison, the smallest ARM Cortex that you can synthesize is 12,000 gates. And let's do an excursion first. What is an MCU? And a microcontroller is it just unifies everything. It's got the CPU, RAM, ROM, timers, peripherals like I/O pins, a UART, serial port, pulse width modulation. Sometimes it's USB, CAN bus if it's for cars, Ethernet. Some chips have A to D converters, some D to A converters, and that results in a system that as an extreme can consist of a single chip. That means you take the chip, you apply power, and it's running. Today, these MCUs are flash-based. They don't require any special equipment to be programmed. Mostly, it's just a serial port. And so the best match for an 8051 is probably not a 6502 processor, but the 6500/1 microcontroller, which, for example, has been used in the Amiga keyboard, but also in the Commodore 1520 plotter. There has been a popular reverse engineering about that, but that's not what this seminar is about. Now, 1T8051 is what TSMC, the largest semiconductor manufacturer on the planet, is calling them. 1T stands for the speed. 1T, 1 clock cycle, is the fastest you can get on an 8051. The original Intel actually took 12 cycles for the fastest command, and so one machine cycle consists of 12 clock cycles externally. 8051 has surprisingly small amounts of memory, 256 bytes internal memory divided into 128 bytes that can be addressed directly, and another 128 bytes that can only be accessed indirect. The smallest one has, the standard code size on the original Intel was 4K. It had 2 timers, which can also be configured as counters, a UART, which is a serial port, without handshake, that is, so 2 pins only, one for receive, one for transmit. 8051 has separated code and data space. That means it can only execute code out of ROM. It cannot execute code out of RAM. So no self-modifying code. It's got 2 interrupt priorities. That's an 8051 property. Dual data pointer is actually a special property of the TSMC 8051. We'll get to that later. Depending on the package, you get up to 40 I/O pins, and some of them are shared with hardware that you can configure to overlay the actual port pins. To continue or to dive into why 8051, it's all about money. I've just collected some screenshots here. If you look for an 8051 development system or just something to play with, you can get it really cheap, like a fully featured development board for $10, something even with a wireless demo board for just over €4 shipped. That is free shipping. Or if you go to the Nuvoton direct page and buy the chips, you can actually buy them under 50 cents. It's just ridiculously cheap, and therefore 8051 is just the industry standard, and will probably continue to be that. There are lots of development tools available. You can choose if you want to develop in C, Pascal, even BASIC is available. KyleC is a commercial compiler, which is practically the industry standard. You will find KyleC implementations or KyleC support for practically every 8051 out there. SDCC, that's the free small device C compiler. But if you want to compare CPUs like we do in this seminar, then you got to go bare metal. So we do assembly, and I chose ASM51. That's a free command line assembler. You don't have any fancy IDE with it. You just edit your source code with a text file, with a text editor, and then run the assembler with a command line. The assembler will spit out a so-called hex file, which is accepted by all the flash tools from the chip vendors. And debugging tools are never source level. You debug really manually. That means you output a string on a serial port on the serial terminal, or you let in LED flash, or watch some I/O pins on a logic analyzer, depending on what you want to do. One of those options. And we've used 8051s for many projects within iComp. Some of them are obvious, like the mouse adapter and the keyboard adapter. Those are obvious microcontroller applications. But for example, the C64 Reloaded Mark II, that's not so obvious. The main purpose of the microcontroller in the C64 Reloaded Mark II is to actually hold the ROMs. So I just chose a version with a little bit more flash and with flash capability from the code of the 8051, so I could spare the external parallel flash. But these are just some examples. This is not supposed to be a seminar about our products, but about 8051 MCUs. So let's look at the programming model. I assume you know a little bit about 6502 already, so I'll just run quickly through that. It's got one accumulator, 2 index registers, you got an 8-bit stack pointer, and there is actually 1 unused bits in the processor status word. You know that the official opcodes is only 156 out of the 256. Most of the undocumented opcodes do something useful. Some just jam the processor, but that's not what this seminar is about. I only outlined the number of opcodes because the 8051 has almost all the opcodes used. It's got a B register in addition to the accumulator, which is used for 2 special commands that we'll get to later. Instead of just 2 index registers, the 8051 has 8 registers and 4 banks of those. That means 32 registers that you can use pretty freely. Stack pointer is also 8 bits. The processor status word has 8 valid bits, and there is no 0 flag. How the 8051 lives without that, we'll get to that later. But one special property that we will always return to in the seminar is that all of the registers, the accumulator, the processor status word, and even the registers, they are all memory mapped, and this might lead to funny bugs on the one hand, but it also gives you quite a few opportunities. Now, the 6502 is a very classic von Neumann architecture. Code, data, I/O, that's all within the same address space. That means you can write code into RAM, you can execute code from RAM, and you can even write code that modifies itself. All the dirty tricks that you're normally not supposed to do. And the 8051, on the other hand, has separated code space, RAM space, and even the RAM space is divided into internal RAM and external RAM with special commands for accessing external RAM. The internal RAM is divided into 2 128 byte pages. The lower 128 bytes are directly addressable. The upper 128 bytes are only indirectly addressable, and they are overlaid by the special function registers, which contain the I/O bits of the 8051. So 3 different address spaces. You got to keep that in mind. Now, after power up, the 6502 will just fetch the reset vector and jump to that address. You would clear the decimal flag because that's not defined after a power up. You initialize your stack pointer, and here's where the first difference is. The stack pointer on the 6502 decrements on a push after it's stored. So it first stores, then decrements. That's called the empty stack approach. The 8051 has the full stack approach. That is, it increments and then the store is executed. The 8051, when it starts, it doesn't fetch a vector. It just jumps to a fixed address, and that is address 0. Now, the first thing you normally do is to put a jump instruction to address 0 because the next vector is already at address 3. You don't want to overwrite that, but that's a detail that you'll find out quickly once you dive into 8051 assembly. Speaking of stack pointer, once again, this stack pointer is part of the memory mapped registers. It's at data address hex 81. If you want to move data around, 6502 always requires 2 commands, a load and a store. It's called a load store architecture. And the 6502 has pretty elaborate addressing modes. You can do simple index address displacement, but even indexed and indirect. While the 8051 is a little bit more scarce, but it has a distinct feature, and that is move architecture. The move command has 2 operands, one source, one target, which is always written as target first. That gets some getting used to and might be part of the human rights thing, but like I said, you're gonna get used to it. Now let's run through these 6 addressing modes real quick. Immediate is, of course, you have the data as part of your instruction. You can move immediate with 8-bit values, like into the accumulator, a register, or directly into a memory location. You can even load the data pointer with a direct 16-bit value. That's although the mnemonic is also move, it's a different opcode. The assembler will do that for you. Don't worry about that. Now you can also do register direct, second addressing mode. That means you can move data between registers and the accumulator, between registers and memory, but you cannot move from register to register directly. However, since the registers are memory mapped, you can do an indirect. Indirect is that's also an addressing mode, so that would be misleading. So you can access registers directly. Next addressing mode is direct, meaning you can move memory to memory. That's what I just talked about. If you want to move from register to register. Now, register indirect, that's when it becomes a little more complex. Your register is pointing to a memory address. So, for example, if register number 1 contains hex 66, your accumulator contains hex 33, then you move data around a little bit more indirect. No need to read that. Final addressing modes. The indexed addressing modes are kind of scarce on the 8051 because there are effectively only two instructions. That is move code indirect from program counter plus accumulator displacement, or from the data pointer plus accumulator displacement. And it is actually as complicated as the opcode suggests, because the accumulator first serves as your offset, but at the same time it serves as your data target here. So in a loop, you must reload the accumulator on every loop run, which might be a little tedious. But then again, it only takes a little bit of getting used to. The move C instruction is move code, and that doesn't move data between RAM or or one of the function registers, but move C, move code, implies that your data source is program memory. That means you can use tables within code space. And the last addressing mode is, of course, implied. That is those are opcodes that have the operand implied, similar to return from subroutine or clear carry on the 6502. Now let's look at one of those accumulator displacement move code examples. If you want to access a table, this is actually a subroutine taken from the Dismo of the ACA 500 Plus. It converts a 4-bit value that is given in the accumulator into an 8-bit value from a logarithmic exponential table, which is required to have a linear brightness control for the LEDs here. What's happening here is I am making sure that only the lower nibble is active. I increase the value by 1 because the subsequent move code instruction will always take the next value, that's where the program counter points, as the offset. And since I don't want the opcode of the return from subroutine mnemonic in my table, I'm just increasing the accumulator here. So this routine takes in a value between 0 and 15, and one of these 16 values will be returned. Similarly, if you want to send out a string on the UART, this routine will do the trick, really just a few commands, but this one uses the move code at A plus data pointer into A. And this one also shows for the first time here how the 8051 is getting around the fact that there is no 0 flag. There is a special command that just says jump if the accumulator is 0 or if it is not 0. This this loop here will just continue until the string, which is pointed to at the D pointer with the data pointer, is 0 terminated. Now we'll get to bit addressing. That is a special property that the 8051 has, the 6502 doesn't have. So bit addressing is possible for a set of memory locations between address hex 20 and hex 2F. So 16 addresses times 8 bits, 128 bits that are bit addressable. There are special opcodes for that. Plus the special function registers that end in nibble 0 or 8. They are bit addressable. Those are, for example, the port bits. And just to give you a comparison between 6502, if the 6502 wants to set a bit in 0 page address hex 20, it requires 3 commands and it'll overwrite your accumulator. But the 8051 just has an opcode for that. That would be set bit 002. So that implies the bits for bit addressing start counting at 0 in address hex 20, and then they just count linear. So the bits within the special function registers, they start at address hex 80. Jumping around in your code. The 6502 can jump absolute, it can jump indirect and PC relative, but only conditional. So the branches inside the on the 6502 are only conditional. There is no branch always instruction, at least not on the NMOS 6502. The 8051 can do a little bit more. It of course can do absolute, but those jump commands are geared towards being very short. You can do a jump to a 16-bit address. You can stay within a 2K space. It can be indexed, it can be PC relative, and here are the examples. I believe I skipped one. No, I didn't. I'm sorry. So the long jump, that's a 3-byte instruction. Long jump or long call. Call is the equivalent of jump subroutine. That can jump anywhere in the 64K code space. Then there is a shortened version, 1 byte shorter, but that needs to stay within the same 2K block. So it will only modify the lower 8 bits of the program counter. You might want to ask, why is there another 2-byte instruction, sjump, which can only jump to a relative address? Well, that's because it can also cross a 2K boundary. So there is all the possibilities to really squeeze out the last byte of your code size, and maybe also execution time on the 8051. A typical jump table in an 8051 would not use an indirect jump in terms of you have an address and that's holding your pointer, but it's going to be a jump table like this. Imagine this is a routine where you jump to with a number between 0 and 7 in your accumulator. Then this routine will select one of these jumps depending on the contents of A when you jump into this, when you jump here. Now this AND makes sure that the accumulator really only has these 3 bits valid. Rotate left multiplies by 2 and makes sure that I jump, because these A jump commands, they are 2-byte commands, therefore I multiply by 2, and then I jump at D pointer, which has been initialized with the jump table, plus A. This construction is very common. Practically every 8051 code has it, so you should have seen that. Conditional jumps in an 8051 are very similar. You can jump if carry is set. You can jump if carry is not set. You can jump if any bit is set. This is very powerful. Like I said, there are 128 bits within RAM and another 128 bits within your special function registers that can all be used as a source for these two jump bit and jump not bit instructions. There is even a third one, very powerful, jump bit and clear if it is set. And here's yet another one, a special one that gets around the lack of 0-bit, jump if 0 or jump if not 0. You might ask why there is no opcode that branches on overflow. Once again, all the registers of the 8051 are memory mapped. That means the processor status word is also memory mapped. It's available to any command that accesses memory. The processor status word is in address hex D0. 0 means that the 0, the second nibble, the lower nibble, being 0 means that the processor status word is bit addressable. So you can use the jump bit or jump not bit commands to branch if overflow or if not overflow. So essentially the same as the 6502. Now, conditional branching is required for loops, and especially for loops, no matter how long. The 8051 has a very powerful command, and that is decrease and jump if not 0. This will decrease the operand by 1. If the result is not 0, it'll jump to the relative address. Relative in terms of 8-bit signed, so 128 forward or 127 backwards. The special thing about this decrease and jump not 0 command is it will not affect any flags. That means you can do calculations within your main loop, and the loop overhead itself will not interfere with the calculations that you do there. And it's available as a 2-byte or 3-byte command. One is using registers, the other is using memory locations as operands. So once again, the 8051 instruction set is geared towards being short and effective. And the TSMC 1T 8051 will execute the decrease and jump not 0 command in 2 cycles, no matter how long, even the 3-byte commands. Value comparison on an 8051 is different from 6502. The 6502 has the compare instruction. If you use that, the processor will do a subtraction internally, but it will discard the result of the subtraction and only keep the result in the flags, like 0, negative, and so on. But the 8051 doesn't have that. Instead, the 8051 has the compare and jump if not equal command. So you can compare the accumulator, a register, or even an indirect memory location to data or a memory location, and jump to a relative position if it is not equal. If it is equal, the carry flag will reflect. I'm sorry. If it is not equal, the carry flag will reflect if the data is larger or smaller than the operand. Here are some code examples. The 6502 will overwrite the flags for it. The 8051 will only overwrite the carry if the value is not equal. So a three-way decision is easily programmed. However, the 6502 is a little bit more powerful here because the CMP command will also set the negative flag. That means the 6502 is also capable of doing three-way decisions this way if your value is a 2's complement signed binary. The 8051 requires an actual subtraction in order to make a three-way decision for 2's complement signed values. So that's where the 6502 has an edge over the 8051, but to be honest, in my own code, I have never used any signed bytes. Let's look at arithmetic. 6502 will add always with carry. The 8051 actually gives you a selection. So instead of, if you know that the values you are adding are small, then on the 6502 you always need to clear carry before you do the the actual calculation. On the 8051 you can just use an opcode that says add without carry. That is not true for subtract. Both the 6502 and 8051 will always subtract with borrow. But on increment decrement, 6502 and 8051 are substantially different. They will increment or decrement the actual values, but while the 6502 will set the flags according to the result, the 8051 will not. So if you're trying to program a loop using increment or decrement, like you do increment and then do a branch after that, this won't work. 6502, you need to multiply or divide manually, but the 8051 has multiply and divide commands, and those are surprisingly fast. These are the two that use the B register, the one that I mentioned in the introduction, and these are the only ones. If you want to do binary coded decimal arithmetics, then the 6502 requires you to set the decimal flag, and that will affect just about anything that the ALU does, while the 8051 gives you the decimal adjust DA opcode, and this just needs to be executed in the right place, and then you adjust your calculations to be binary coded decimal. Let's look at logic operations. The 6502 can shift the accumulator through carry, but can also shift directly without going through carry. And it can do the logic operations and or exclusive or, while the 8051 can do all that and more. It can do logic operations not only on accumulator, but also on registers, memory locations. It can even do that with indirect addressing. There is a special opcode that swaps the upper and the lower nibble of the accumulator. And for every bit of the 256-bit addressable locations, there are set, clear, and complement commands that can be executed directly without tedious loading, changing, and storing back. So on the logic operations side, the 8051 is really more powerful. But when it comes to interrupts, that's where the huge differences start. The 6502 is really comfortable. It will store the program counter and the status on stack. So what you need to do is maybe save accumulator X and Y, depending on what you need in your service routine, do your stuff, and go your way. But if you want to transfer this knowledge to the 8051, you're in for weird bugs, because the 8051 will only push the program counter on stack, just like the jump subroutine command. So if you think interrupt on an 8051, you need to think subroutine, jump subroutine. So in order to have the same that the 6502 is doing, you need to push the processor status word to stack manually. However, you might be able to write an interrupt service routine where this is not required because there are so many commands that do not affect the register, the flags. However, it's just good practice to start off with an interrupt service routine that saves the processor status, because that's an optimization that you can always do after your code has been is known to work. First, make it work, then make it fast. So, next, instead of saving the accumulator and register contents to stack, on the 8051, you might as well choose to just switch to a different bank. And on the TSMC 1T8051, you can even choose to not store the data pointer, but just to switch to the other data pointer, which is a specialty of the 1T8051. So what does it look like in code? 6502, if you enter your IRQ service routine, you clear the decimal, because you never know if your main routine has used decimal flag or not. Of course, you as the author of the code will know, so this is optional. Then if you want to save anything to stack, it always needs to go through the accumulator. And then the 6502 needs to find out what's the IRQ source. On a Commodore 64, for example, you have two IRQ sources. That is the video chip and the SIA chip. So this might be necessary here with the, this is what my example here stands for. You load the IRQ status of the peripheral chip and check, well, was that you? And then branch into the right interrupt service routine. And then when you exit, you need to pull everything again through the accumulator. That's the big difference on the 8051. Stack operations can be pretty much anything in memory, not just the accumulator. So I can push the processor status word, next I push the accumulator, and next, oh no, I don't push any registers. I switch to a different bank because the bank is selected with 2 bits in the processor status word. So by setting these 2 bits here, I switch to a different register bank. This command here will switch to another data pointer on the 1T8051 by TSMC. And when you're going back, you pop the accumulator and you pop the processor status word. And at the same time, it will also restore the register bank that has been set before. Of course, the routine assumes that the main loop is using data pointer number 0 and the IRQ is using number 1. Another specialty of the 8051, you see this origin assembly instruction here. That means this code shall be assembled to a fixed address. What you don't see in this interrupt service routine is a check, where did the IRQ actually come from? And that's another property of the 8051. Depending on the interrupt source, the jump target is different. In this case, it's timer 1 IRQ. It will always jump to address hex 1B. And for every interrupt source, there is a fixed address. So if code is executed here, you know for sure that the interrupt source has been, in this case, timer 1 IRQ or pin IRQ or whatever. Now the 8051 handles interrupt priorities slightly different, slightly different than the 6502. On the 6502, NMI always has higher priority than the IRQ. But on the 8051, interrupt priorities are programmable. That means I can put timer 1 IRQ higher than a pin IRQ or vice versa, depending on the application. And I will always have, like I already said, I will always have a fixed address where the CPU is going to jump to. And my pin IRQs are even programmable to be negative edge sensitive or to be low level sensitive. Whereas the 6502 will always have the IRQ level sensitive and the NMI is always edge sensitive. So that's also more flexible on the 8051. That should already give you a nice head start on your first 8051 assembly. However, there are some pitfalls on the 1T 8051. They might apply to other 8051s as well, but this TSMC implementation is so popular. I'm just mentioning a few that I encountered over the years. First of all, if you want to see your debug and you want to use a UART, then of course you also need to initialize your pins. Of course, the transfer pin needs to be programmed as an output, but although you don't see any 1 or 0 that you set on that port bit, because it is then multiplexed with the UART, you need to set the port bit to 1. Otherwise, the UART output is not seen on that pin. And knowing that might save you an hour or two of debugging. Now, if your circuit requires a pin to be low on power up, then the 8051 might not be the very best choice, because most of the 8051 implementations out there will have the port bits configured as quasi bidirectional outputs and with a logic 1 level, so with a weak pull up. So if your circuit requires it to be 0, then you carefully need to select your chip. Some of them can only program certain pins to be 0 on power up, but those are available, but you need to do that really early in your design. Otherwise, you will need external components to get around that. Now, if you choose one of the pins to be a reset pin, then the 8051 is just the opposite of 6502. The reset pin of the 8051 is active high, and the 6502 is active low. That just requires some getting used to. Once again, it's just a minor difference. But for example, bigger differences come in the Nuvoton PWM, the pulse width modulation controller. Pulse width modulation is when you, for example, want to control an LED brightness or motor control or something. This controller can also issue an IRQ, but if you choose your pulse width to be very short, then the IRQ just doesn't happen if it is too short. And that is something that also causes funny bugs, just so you're prepared if you want to play around with that. Watchdog, very useful thing, but how you need to keep in mind, when the watchdog is activated, there is no way in hell you can stop it. You need to feed it, otherwise it's going to bite. And another pitfall, the last one, that has cost me quite a few hours of debugging after moving to a different processor. The faster 1T8051 implementations are kind of pipelined. So if you output a value on a port pin and have your and then expecting a response from external logic in the command right after the port pin setting, then this next command might already be executed while the port pin is still toggling or will toggle in one of the next cycles. This can be easily remedied by a NOP before this jump bit or jump not bit command, but you just need to have the idea. So again, might save you some time in debugging. That leaves me to the thanks section. First of all, revision team, thanks for organizing this. I know this is challenging, but hey, you're gaining some experience, second year in a row already. I gotta say thanks to Peter and Tobias, who both have experience in 8051 coding, and of course they know the 6502 inside and out. They proofread these slides, so thanks to those team members. I have recorded this seminar using the OBS software, so thanks to those guys for making the software. Topi, a demo scener who you all know, he hinted me at STC microcontrollers for the first time. So they make these 8051s at TSMC, actually. These slides were made using LibreOffice, and I will make them available as a PDF, either on my page or on the revision pages. We'll find a way. And that leaves me for the conclusion. 6502 is definitely superior when it comes to 2's complement signed arithmetic. It has a lot more addressing modes than the 8051, especially if you do indirect and indirect indexed. That requires some detours on the 8051, where the 6502 makes it really simple. But I am hoping that I could show that the 8051 is not as painful as the reputation suggests. So Kai, I don't believe it's violating human rights. But it's superior in unsigned arithmetic. I believe it's vastly superior in logical operations, especially the bit operations are very, very handy. And conditional branches, especially with bit addressing, once again, that comes in very handy. And the flexibility in interrupt handling, programmable priorities, and no need to probe for an interrupt source and stuff. That is really a nice thing over the 6502. So all in all, I would say if you know the 6502 already, then 8051 is mostly harmless. And my hope is that maybe I see some wild demo next year. Who knows? So I wish you guys, well, first of all, thanks for your time. Thanks for listening. Thanks for making it up to the end. I wish you guys a very nice revision 2021, remote vision. Once again, thanks. Have a good one.